All right, can everyone see my slide here?
Yes, sir.
All right, so remember, a sequence is a list, and a series is summing up all the terms of the list. Never lose sight of that when we get into all these techniques for convergence. So we said there was the sequence, and then you can take that sequence and make it into a series by adding them all up. And then from that series or the sequence, we can build a sequence of partial sums. All right, so sequence looks like this. It's just the list. First in the list, second in the list, an ordered list. So to be more specific here, we'll often put the starting value, which for a sequence is normally 1, so that we are actually, the value of I is like the number of in the list, right? First, second, third, so I is 4 when it's the fourth. And then if it's an infinite sequence, then we have telling us that we're going to apply whatever formula we have, starting with I equals 1 all the way into infinity. And a sequence is the list. What about a sequence of partial sums? Is that a sequence? Is that an ordered list of numbers? Yeah, it's still a sequence, right? It's still a sequence. It's just a specific kind of sequence. All right, so it's still a sequence. Okay, so then we said a series is when? What? We said there were 2 ways to notate that. There was like the calculus way, the big boys way, right? So it's you use summation symbol, I equals 1 to infinity, and then that's our formula for the ith term of the sequence. And then we said, but we know what that means. That means just add up all these terms. Okay? If it says dot, 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 so if it says dot, 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 what does that mean? It just keeps going. So it's an infinite series. That means you keep adding up the terms without end. And that's also, we see that here, that you're going to add up an infinite number of terms. Start with I equals 1, then I equals 2, then I equals 3, but keep going without end. Okay, and then we said we could make this sequence of partial sums. And we do that by the first partial sum is the sum of the first 1 terms. The second partial sum is the sum of the first 2 terms. The third partial sum of the first 3 terms, etc. Fourth partial sum of the first 4 terms. Fifth partial sum of the first 5 terms. Okay? And what was important about the sequence of partial sums relative to the series? We had a big conclusion about the relationship of the sequence of partial sums and the series, which is adding up all infinitely many terms. What was that important relationship?
The sequence of partial sums tracks the accumulation of the series for a given index.
Okay, it's good, right? So it's tracking like building the series, right? Like, so each term in the sequence is like building the series one term by one. You can keep adding on one more. What else could we say about the sequence of partial sums and the series?
If we take the limit of the sequence of partial sums, then that's going to give us the sum of the series, or the series.
Right. The limit of this sequence, right? We talked about limits of sequences. The limit of the sequence, like what this sequence is heading for, right? What this sequence is heading for in the end. Well, think about what the sequence is. You keep adding on one more term. You're building the series one by one by one. So if you take the limit of that, you're going to get the series. It's gonna be the whole series. The limit, or like if there was a last infinite term of this sequence of partial sums, it would be the series. Okay? What about a partial sum? So what about the fourth partial sum? So we saw that the fourth partial sum is, or the fifth one is the one I'm showing here. It's just a finite number of terms added together. And you stop, so that's the fifth partial sum. How can I write that with summation notation? The fifth partial sum. I'm going to still be adding up the terms of the sequence, starting at I equals 1. What's the difference?
This now infinity, you replace it with 5.
Yeah, so now it's just going to go, I would just want I to go from 1 to 5 and stop. And that's what this top number means, the last term I'm going to take. So I'm going to go 1, I'm going to take the first term, the second term, the third, the fourth, and the fifth. And this sigma means add them all up, but stop after 5. So this would be a partial sum. So an infinite series would our last, there is no last term. That's why I put an infinity there. A partial sum, this tells us which values of I we're going to evaluate the formula and add together. And so if we do the first from I equals 1 to 5, that's the fifth partial sum. Okay, questions on this review?
I'm not gonna understand.
Any questions? Okay, we'll see if we got it. All right, so we were talking about the ratio test. Let's go to that. Where's the ratio test here? I think it's coming up here. Where is it? Maybe this one? Yes. Okay, so we're talking about the ratio test, and that was for absolute convergence. What was absolute convergence? That was when, if it's like an alternating series, if you take the alternating effect off, right? So,
Hey, I already gave you a treat.
hey Elena, your microphone is on. Elena Rios. All right, so given a series, call it Ci like this. Let's say the series converges absolutely if what? You make all the terms positive. So there's a potential that some of the terms could be negative here, and maybe that could be helping it converge, right? Because you're gonna add some and subtract some. So if we're talking about getting a finite sum, subtracting some would be immensely helpful, right? In having this thing sum up to some real value. But if you take away any terms that are subtracted, right? Make them all positive, and it still converges, then it's kind of like a stronger convergence, right? It's like it doesn't need that subtracting effect on half the terms or some of the terms to converge. It'll do it even if they were all positive. That's what absolute convergence is. So you think of absolute value. Absolute converges, the absolute value of all the terms. Okay, and so we introduced this test called the ratio test for absolute convergence last time. We did an example. Let's do some more examples today. We said that you look at what? You look at the sequence. You build the sequence from the sequence that you're adding together. So you have your series, and you're going to take those terms of that sequence, and you're going to build this sequence. And do you remember what these ratio represented? What was this ratio of AI plus 1 over AI? It's key. So
It's the ratio of the next term of the sequence over the current term.
right. So it's going to be the ratio of every next term to the current term. And what was that? Do you remember what that was? What it represented?
Wasn't it R?
Well, it's like R, right? So it represents the multiplier. This is the sequence of multipliers to get from one to the next, which is like R. One term to the next. And that's like R. The difference is with R in the geometric series, that R stays constant. That's what makes it a geometric series. It's this constant value r that you keep multiplying by to get the next term. Here, it's like we're taking any sequence and we're building a new sequence of multipliers, and those could change, right? So what you need to multiply to get to the next term could change if it's not geometric. It will change if it's not geometric. So then we look at the limit, right? We look at that sequence and look at the limit. If those multipliers are honing in on a value less than 1, then it's like the sequence is becoming geometric with r less than 1. That's why we're looking at the limit of this. And if the limit of the sequence of multipliers is a value less than 1, then we say the series is becoming like it's geometric with an r value less than 1. So
do you mean that like the multiplier is decreasing each time?
no, it doesn't have to be decreasing. It just has to head to, so like if r was 3/5, the multipliers don't have to decrease to 3/5. They just have to kind of hone in on 3/5. So they could be increasing to 3/5. They could be less than 3/5 and getting closer and closer to 3/5. As long as the limit is 3/5, then in the end, it's like we're multiplying by 3/5 over and over again to get the next term. And so those terms are going to shrink.
Okay, thank you.
Does that make sense?
Yes.
Okay, cool. So it's like, so that ratio is like a changing r. It's like a changing r, but if it hones in the long run on a particular value of r that's less than 1, then that's going to converge because it's like in the long run you've got this geometric series. Likewise, if that limit is greater than 1, it's going to diverge, and then the test doesn't yield a conclusion if L equals 1, you got to do something else. You got to reach back into our toolbox and figure something else out. Ratio test isn't helping with this particular series. Okay, so let's do examples here. Okay, we did that one last time, so you can check the video. Here's a new one. Okay, and so we're going to form that, We're going to form that sequence of multipliers by making this ratio and see what those multipliers do, right, by evaluating the limit of that sequence. Okay, and so remember what I said last time is, instead of starting by writing it as a fraction like this, which you can do, it's just easier to just start by writing it as the product of the I plus first term times the reciprocal of the ith term. So we can always start that way, and it saves a lot of writing at the beginning. Okay, so the ai plus first term is going to be -1 to the I plus 1, 7 times I plus 1 squared, I plus 1 cubed, plus 4. Right, so the I plus first term is going to be this thing with I plus 1 plugged in, right? Because the sixth term is just what you get when you make I equals 6. And the 10th term is what you get when you make I equals 10. So the I plus first term is what you get when you make I plus 1. And then we're going to multiply by the reciprocal of just the ith term, that is the ith term. So we got I cubed plus 4. And -1 to the I, 7i squared. Okay, so now we got getting kind of a complicated expression here. So the way we're going to evaluate this limit is we're going to put the things that are like together. So we're going to combine, think about these two in the limit together, and then think about these two together in the limit. And then what is -1 to the I plus 1 over -1 to the I? So what does it mean to multiply? Actually, we're multiplying a bunch of -1s together here, and in fact, one more than we have in the denominator.
So is it -1?
yeah, the result is going to be just one more negative 1 in the top, right? This is, if you imagine a bunch of negative 1s multiplied together and a bunch of negative 1s multiplied together, and this is actually one more in the top. So we can just make that, or just cross this whole thing out and cross that exponent out, and we have negative 1. But then we're going to take the absolute value. So when we take the absolute value, it has no effect. Now, it will have an effect if it's a number other than negative 1. So if it, like we saw in the example last time, I think it was negative 3. That you can't disregard, because now you're multiplying this whole thing by 3. That could be important. But if it's just the alternating term, the negative 1, then always that negative 1 alternating term will just kind of go away, because you'll have one more negative 1, and it'll be the absolute value of it, and so then it has no effect. Does that make sense? So in evaluating this limit, we're looking at what's the limit of I cubed plus 4 over I plus 1 cubed plus 4. So what's our leading term there? I cubed. What's our leading term down here? I cubed. So as I goes to infinity, what's the limit of that sequence? 1. I cubed over I cubed. It's just going to be 1 as I gets big. Same thing here. I got 7i squared, and I got another 7i squared. Limit? 7i squared over 7i squared.
So 1.
1 also. So the absolute value of negative 1 is 1. The limit as I gets big for this thing is I cubed over I cubed. That's 1. 7i squared over 7i squared. Everything is 1. So this goes to 1 as, so that's the limit is 1. And so what does that tell us?
Indeterminate.
Nothing, right? So here's a case where the ratio test is not helpful. Okay, so it was good practice to practice this limit and set this up, but we didn't make any progress other than practicing and doing an exercise of a limit of a sequence. So then we got to go back to this and do something else. So we look at this and we say, okay, we got an alternating series, and we got 7i squared over I cubed plus 4. Is there anything in our toolbox that for which this series applies? So we got what? P series, geometric series, comparison test, alternating series test. Those are our main tools right now. So what of those things? Is it a P series? No, not quite, because of this plus 4. Because of the plus 4 in the denominator, it's not a P series. But it looks like it's similar. It's definitely not geometric. So what about this? What about 7i squared over I cubed plus 4?
Alternating test?
Can we use the alternating test? What about 7i squared plus I cubed over 4? All the terms are positive. What about this sequence? 7i squared over I cubed plus 4.
Equals convergence.
It's a decreasing sequence.
It's decreasing. They're all positive. And what's the limit of the sequence?
0.
0, right? Definitely 0, right? Because I got a higher degree in the denominator than the numerator. So all the conditions are met for the alternating series test. You got positive terms that are decreasing, and they decrease to 0, and then it alternates. Conclusion.
It will absolutely converge to 0.
Is the alternating series test a test for absolute convergence?
It's that it's going to converge to 0 because the sequence converges to 0.
So the series will be 0? Will the series be 0?
No, the sequence will be converging to 0.
Yeah, the sequence converges to 0, it decreases to 0. and it's alternating, therefore, what about the series?
It can only converge when it's alternating.
All right, we just got to get to convergence first. Yes, this converges by alternating series test. It meets the requirements of the alternating series test. We have positive terms that decrease, and the limit is 0, and it alternates, therefore converges by the alternating series test. Now the question is, does it converge conditionally or absolutely? Does it converge conditionally or absolutely?
Conditionally,
So, why conditionally?
purely because we had to use the different conditions that alternating series test has.
Well, so just because it qualifies for the alternating series test, it doesn't give us that is not how we can conclude that it converges conditionally or absolutely. It just the alternating series test is not a test for absolute convergence, so it doesn't tell us one way or the other. It just can tell us if the series converges or not. So to see if it converges absolutely, we can look at this series. Take off the alternating effect. What about this one? Does this converge?
Yes.
Okay, I have one vote for yes, that this series converges.
I'm worried that it looks too much like a harmonic function.
Okay, why, Nathan? Why does it look harmonic?
Because if you were to cancel out the I, like in the grand scheme of infinity,
Right.
so it's really I squared over I cubed, and it will be 7 over I, which is slightly larger than 1 over I, which is technically a harmonic series, which we found.
Exactly, right? So this sequence, as I gets big, is basically 7 over I. It's like 7I squared over I cubed, which is maybe,
Harmonic series.
yeah, it basically is the harmonic series 7 over I, which, and we know that that converges to 0, but it's like a p series with I equals 1, so the series will not converge, right? So we took the absolute value off to text for absolute convergence, and we see that the sequence in the long run is essentially harmonic. And if it's essentially harmonic, then this series diverges. By limit, this is the limit comparison. I'm looking at the limit of my sequence. This is like a comparison. I'm looking at the limit of my sequence, and the limit of my sequence is like 7 over I, which that series diverges. Therefore, by limit comparison, this diverges. And this was to check for absolute convergence. So, does this series converge absolutely?
No.
No. So it converges conditionally. It passes the alternating series test, so it converges, but it's needing those, because it's like harmonic, it needs the alternating terms to save it and get it to sum up to a finite value. Okay? But if you take that thing off, it diverges because it's like the harmonic series. So this one is conditionally convergent, or converges conditionally, is the conclusion.
Actually, Professor, we only did all of this because the ratio test was indeterminate.
That's right. The ratio test gave us this L equals 1 case, so we had to go back and apply something else. So we could apply the alternating series test to tell us that it converges, but then we had to check to see about condition or absolute convergence, which was a no, right? This is essentially turns into the harmonic series in the end, which diverges. Therefore, this series is requiring the flip-flopping negatives in order to converge. Okay, did you catch that? So lots of really important principles there. Any questions? So, for instance, going back to this, if this was 7i squared over I to the 5th plus 4, the alternating series test would say, yeah, that converges. And then when we took the alternating off, it would also converge because it would be like something like 7 over I cubed or 7 over I squared. So that would converge conditionally. So again, I'm just restating that the alternating series test isn't a test for absolute convergence. You can get, it can converge by the alternating series test. It still might converge conditionally, or it might converge absolutely. In this case, we had conditional convergence.
Professor,
Yeah.
if we had the same power, then we would have a limit close to 7, right? Or that way just wouldn't converge like conditionally, right?
So now you want 7i squared over I squared plus 4?
Yes.
What about that?
Well, in that case, that's basically the same power. So if we didn't have the 4, then we would say our limit is 7.
It's 7.
Yes.
Okay, and so then what happens? In the sequence, in the end, we just end up with a bunch of 7s.
Right.
So what about the series?
Well, then it doesn't converge.
No, right? That's just the divergence test. If your if your sequence goes to something other than 0, if your sequence doesn't go to 0, game over. All this stuff is, and I should have said that first. The very first thing we should have done was make sure this thing goes to 0. And then if it doesn't go to 0, we could have saved all this effort, right? Well, if it didn't go to 0, then the ratio test would have told us that. But yeah, always check, use the divergence test first. If your sequence doesn't go to 0, just put your toolbox away. We're over. It's done. This thing will diverge. If the sequence goes to 0, then that's when things get interesting and we can apply all these tests that we have.
Series test, is that the only one that doesn't tell you absolutely if it's converging or diverging?
What's that?
Is the alternating series test the only one that doesn't tell you absolutely whether it's converging or not?
No, just our rule for the P series or our rule for a geometric series. Those weren't like for absolute convergence. Those were just for convergence. So the tests for absolute convergence are either the ratio test or slap a absolute value around your terms and then evaluate that series. Those are the two tests we have for absolute convergence.
Okay, thank you.
Yeah, sure.
I have a question.
Sure.
So the absolute convergence test, so it's telling us that whether or not the alternating part is there, that the series will converge. Is that what it's telling us?
Absolute convergence means if you take off the negative terms, if you make them all positive and it still converges, then it has absolute convergence. Absolute convergence means it doesn't require the alternating effect to help it converge. It even will converge if all the terms are positive.
Okay. So, all right. Just checking.
Okay.
Thank you.
All right, we need to do some more examples here. Okay, here's one. Factorials. We gotta remember our factorials. So here we go. So we're gonna set up AI plus 1 times 1 over AI. And what is that? Negative 1 to the k plus 1. 2 to the k plus 1 over k plus 1 factorial. So that's the k plus first term. Now times the reciprocal of the kth term. Okay, how are we doing? Make sense? So, and again, what is this? This is the sequence of ratios of multipliers, right? So it's the sequence of multipliers to get to the next term. And the ratio test is testing to see if those multipliers are turning this sequence into a geometric sequence. All right, so here we go. So we can compare like things. So first of all, we know that the -1 to the k plus 1 and -1 to the k after the absolute value doesn't mean anything. It goes away. If that's not a -1, you have to keep it. Okay? Be careful. The only way you can just disregard is if you truly have -1 to your index. If it's any other value, you need to keep it. Okay? 2 to the k plus 1 over 2 to the k. So 2 to the k plus 1 over 2 to the k.
We're gonna have another 2 on the numerator.
1, 2, and that's 1, 2 is left in the numerator, right? So k plus 1 2's multiplied together. So this is a list of 2's multiplied together. And here's another list of 2's multiplied together. We got one more in the top. So we're just going to have a 2. What about k factorial over k plus 1 factorial? What is?
We're going to have a k plus 1 in the denominator.
Yeah, so k plus 1 factorial is going to be k plus 1 times what? K times?
K minus 1.
K minus 1, right? So factorial, again, review. It means start with the number and then multiply by the next lowest whole number and then multiply again by the next lowest whole number until when?
Things start to cancel.
So 1.
All the way to 1. Every factorial multiplies all the whole numbers starting from that number all the way down to 1. And then notice within k plus 1 factorial, what do we have?
K factorial.
K factorial. Every lower factorial is a factor of the factorial that you're looking at. So 3 factorial, 4 factorial, 5 factorial, 10 factorial are all factors of k plus 1 factorial if k plus 1 is greater than 10. So look at that. So there's k factorial, and this whole thing is k factorial, so it goes away, and we're left with
K plus 1.
K plus 1.
denominator. Okay, and then we're going to take the limit as k goes to infinity. What's the limit?
0.
0. Nice easy limit there, right? Big denominator is going to go to 0. That sequence goes to 0. Conclusion?
We can keep going on and it converges, but we need to find out how it converges. Or no, never mind.
It just converges absolutely.
Yeah, so this is a test for absolute convergence. If L is less than 1, then the series converges absolutely. So these multipliers are getting closer and closer to 0. So that all it needs to do is get to a number less than 1, and it will converge. Well, these multipliers are getting closer and closer to 0, so this is going to converge super fast, right? Because the number you're multiplying by in the end is essentially 0. So it's like after a while, it's like you're not adding anything on at all because it's like adding on a bunch of zeros. So this converges absolutely. So even if this were 9/10, right, it would converge absolutely because you keep multiplying the previous term by 9/10, and so it's getting smaller and smaller. So these multipliers are going to 0, so that just converges super fast. Questions on this example? Okay, let's do another one.
Hey, Mark, I got a couple of questions in the chat about why that last one, why we do not look at it like it's the harmonic series. It's probably worth talking about.
Well, that's this is not the harmonic series. The harmonic series, what's the harmonic series is the multipliers, right? So what was it? 2 over k plus 1?
Yes.
So 2 over 1 plus 1. 2 over 2 plus 1. 2 over 3 plus 1. 2 over 4 plus 1. So what the harmonics, where the harmonic series is showing up in this, it's not that the series is the harmonic series. It's that the multipliers to get to the next term is like the harmonic series. So we're not analyzing the harmonic series. We're not asking if this series converges. We're setting up a new sequence to tell us if this series converges. And this new sequence is a sequence of multipliers to get from one term to the next. So yes, that sequence of multipliers is like the harmonic series, and those go to 0. So in the end, so going way out here, say the millionth term, it's like you have your multiplying by 0, because it's the harmonic series. You're multiplying by 0. You're multiplying by 0 to get the next term. So what are all these terms going to be? They're essentially going to be 0. So this sequence that we create is not the series that we're analyzing. We're analyzing this series, which is not harmonic. So the sequence that we created was the sequence of multipliers, the one that's like the R in the geometric series. And we found out that that sequence, yes, that sequence is like the harmonic series, which tells us that these multipliers are going to 0. Does it make sense?
Yep.
Those who were asking in the chat.
Yes.
Okay, great. Here we go. Next one. Another factorial. So here we go. A little faster here. So because we know that's going to go away, so I'm just going to disregard that now. If it's not a -1, if it's some other number, like a -3 or -10 or something, you need to include it. But with -1, we can disregard it. So we're going to have k plus 1 factorial over 5 times 3 k plus 1 times 5 3k over k plus 1 factorial. Are we good? So what about the k plus 1 factorial and k plus 1 factorial? What will happen with that?
It'll cancel out and we just have k plus 2.
Just 1k plus 2 in the numerator, right? Okay, now what about this? You gotta be careful here. 5 to the 3k. And what is 5 to the 3 times k plus 1? That's 5 to the 3k plus 1?
3.
It's 3. So because this is 5 to the 3k, evaluated at k plus 1 gives us what? 3 more 5s in the denominator. So we're going to have 5 cubed. Not just 1 5, not 1 more 5, but 3 more 5s. Right? So I have 3k number of 5s. I have 3k plus 3 number of 5s. So that means 3 more 5s in the denominator. Okay? Conclusion? What does this do as k goes to infinity?
Goes to infinity.
Right? That just gets big, right? K plus 2. No power of 5s is going to save that, right? K is just getting big. Conclusion? Right? All that limit needs to be is greater than 1 for it to diverge. This limit is infinity. So the multipliers on the terms are going to infinity. So this diverges badly. Right? So this just gets really, really big. And so what it shows is that showing us that factorials get much, much bigger than powers. than powers of a number. Factorials, right? Because this is just repeating multiplying by 5. But when we multiply by here, it gets bigger and bigger and bigger, right? Because as you go on to the next one, you're multiplying the next bigger number, right, to a factorial. Questions on this one? I got one more to do. All right, one more. More complicated? I want to do it. Here we go. So again, -1 to the j we can disregard. So I'm going to have 4j minus 2. Sorry, 4j plus 1. Minus 2 cubed times 6 to the j plus 2 over 3 times 2j plus 1. Right, so this is the j plus first term. Everywhere there's a j, I'm going to put j plus 1. And then the reciprocal of the actual, just the sequence. Okay, how many more? So this one, I'm going to have, basically I'm going to have 4j cubed is my leading term here. 4j cubed is my leading term. What's my leading term here?
4j cubed.
Also 4j cubed, right? The biggest term I'll get here is I'm going to get, this will be 4j plus 4, and so 4j cubed. So what about combining those? What's my limit combining those? 4j cubed and 4j cubed. 1, right? So combining, putting these together and looking at the limit, that's 1. How many more 3's do I have in the denominator?
2.
2 more 3's in the denominator. How many more 6's do I have in the numerator?
1.
1. 6/9. Oh, I should actually, so this is actually going to. We took the limit, right? I took the limit and we said that that limit is 1. So this, this is approaching as I goes to infinity. Conclusion?
Convergent.
Converges absolutely. And what do we say? This is becoming like a geometric series with what?
And R value of 2 over 3.
Yep. So this in the long run is becoming like a geometric series where R is 2/3. And if we know that that converges. So the multiplier to get to the next term of this series gets getting closer and closer to 2/3. So it's like in the end, we're always adding on 2/3 of the previous term. And that sequence will go to 0, right? So that what you're adding on will go to 0 rapidly enough for the whole series to converge to a finite value. Any questions on that one?
Yeah, if it becomes like a series with an R value of 2/3,
Uh-huh.
does it also does it also equal the same value?
No, it will not. The A over 1 minus R?
Okay.
No, it will not. It would have to use the A over 1 minus R, the multiplier has to be 2/3 for the whole series. So
Okay.
we can't use the fact of what the geometric series sums up to. That won't work. But we can make the conclusion about convergence if the multiplier gets the limit is 2/3.